Welcome back, students. Welcome to the lecture 7 in the lecture series of FIR filter design. In this particular lecture, we shall discuss about the third type of design technique, that is through frequency sampling method. In the last lectures, we have discussed about two other methods, that is about the Fourier series method and windowing method or windowing techniques, that what we have used for the design of linear phase FIR filters. And in this particular lecture, now we shall see this frequency sampling technique for design of FIR filters. Before directly starting with the procedure, I would like to add some points where the idea of design of this FIR filters by frequency sampling technique comes from. In this method, the ideal frequency response, that is the desired frequency response, is generally sampled at sufficient number of points, that is n points in the n points. And these samples are the DFT coefficients of the impulse response of the filter. Hence, the impulse response of the filter is determined by taking the inverse DFT in this case. The impulse response that is obtained by taking the inverse DFT of DFT is generally represented as h of k, capital H of k, and for practical realizability, the samples of this impulse response should be always real. But this can happen if all the complex terms appear in complex conjugate pairs. It can only be observed that the complex DFT coefficients exist only as conjugate pairs, and this suggests that the terms of h of k can be matched by comparing the exponentials. The term h of k e power j2 pi nk by n should be matched by the term that has the exponential e power minus j2 pi nk by n as a factor. With this little introduction, now just we shall move forward for the procedure or the steps in designing FIR filters using this frequency sampling techniques. The first step is to choose the ideal or the desired frequency response from the given specifications in the design problem, and clearly note down the HD of e power j omega. And in the second step, we need to sample the desired frequency response HD of e power j omega at n points. The n points are generally given in the design problem. We need to compute all those n samples of HD of e power j omega by taking omega is equal to omega k, that is nothing but 2 pi k by n, where k takes all the values from 0 to n minus 1, and we shall represent this as h of k. H of k is nothing but the sampled version of HD of e power j omega with omega values equal to 2 pi k by n. And in the third step, we will be computing or calculating the n samples of impulse response h of n by considering the inverse DFT of the h of k. Generally, whenever n is odd, impulse response is generally calculated as h of n is equal to 1 by n into h of 0 plus 2 sigma k is equal to 1 to n minus 1 by 2, the real part of h of k multiplied with e power j2 pi nk by n. And in the fourth step, here Re represents, in this third step, that what I have discussed now, the expression, the Re refers to this real part, okay. And in the fourth step, we consider the Z transform of the impulse response h of n to get the filter transfer function h of z, and h of z is simply calculated as a Z transform of h of n from n is equal to 0 to n minus 1. Now we shall see an example problem, an example design problem using frequency sampling technique. In the given design problem, has asked to design as a linear phase low pass FIR filter with a cutoff frequency of 0.5 pi radian per sample by taking 11 samples of ideal frequency response. Actually, most of the times here design method is also specified in the problem itself, but however here in this case now we are since we are covering this problem under this frequency sampling technique, I assume that this has to be designed using that frequency sampling technique itself. Now the desired frequency response, since we are asked to design a low pass filter with a cutoff frequency of pi by 2 radian per sample, we can simply write it as hd of e power j omega is equal to e power minus alpha j omega within frequency range from 0 to pi by 2. Since as we know that this is generally periodic in frequency, generally I also write that it is from pi by 2 to 3 pi by 2 it is 0, but from 3 pi by 2 to 2 pi it has once again a lowable frequency range. Now by taking 11 samples of ideal frequency, therefore now the center of the symmetry lies at n minus 1 by 2, which is equal to 11 minus 1 by 2, and it is going to be 5 in this case. Now since we have already identified the desired frequency response, we shall sample the hd of e power j omega in order to get our h of k. I am trying to identify this h of k by sampling hd of e power j omega at 11 equidistant frequency points, because we were said about n as 11. Therefore I consider some 11 equidistant frequency points in a period of 2 pi, and it comes out to be omega k is equal to 2 pi k by n, which is equal to 2 pi k by 11, where k is equal to 0 to 10. Therefore, calculating those different values of frequency point, I observe that frequencies are given as a multiples of 0.18 pi, 0.18 multiples of pi. Therefore, we have it as 0, 0.18 pi, 0.36 pi, 0.55 pi, 0.73 pi, and so on until 1.82 pi, within the range of from 0 to 2 pi. I identify around 11 points, 11 frequency points, or the 11 samples, and also I was able to see that from the above calculations that for k is equal to 0 to 2, it lies within the range of this passband from 0 to pi by 2, and from 3 to 8 samples whenever we are calculating, they lie in those stop band region from pi by 2 to 3 pi by 2, and for k is equal to 9 and 10, it lies once again in the passband region from passband region from 3 pi by 2 to 2 pi, and therefore the sampling points on this ideal frequency response are now given as something like this. Since we do have identified that the only 3 points are there in the ideal frequency response and here in the passband, and similarly the last 2 points 9 and 10 are also on the passband side, I identify my structure something like this with 0, 1, 2 with passbands, as well as all the other values are considered to be 0 since they are in the stop bands, and once again the last 2 points with a unique values of 1. And now I identify this h of k, the sampled version of hd of e power j omega, the sampling points of hd of omega, and with their corresponding magnitude spectrum, magnitudes equal to unity in this case, and for all those values lying in the stop band equal to zeros. Therefore, I have sampled my hd of e power j omega and identified h of k successfully, and therefore now h of k can be defined simply as a sampled version of hd of e power j omega, which can be written as e power minus j alpha omega k. This is the ideal way of representing your h of k with respect to the ideal frequency responses, and in this case alpha is 5 and omega k was identified as 2 pi n by 2 pi k by n, and here the 2 pi k by n value is taken as 2 pi into k by 11, where k takes all the values from 0 to 10. But fortunately, if for 3 k is equal to 3 to 8, we have already identified that it is equal to 0, and for 9 and 10, once again it is e power minus j alpha omega k, which can be written as the same expression here. And these are the values of h of k now, and now we shall find out the impulse response h of n by using the equation, the impulse response equation, which can be written as 1 by n into h of 0 plus 2 sigma k is equal to 1 to n minus 1 by 2 Re of h of k into e power j 2 pi n k by n, where Re represents the real part of this h of k into e power j 2 pi n k by n. And this can be used for computing the n samples of the impulse response h of n. Whenever this particular equation holds good whenever n is odd, and similarly this will be also holding good for n even too, but however the impulse response value h of n by 2 will be equal to 0 whenever n is even. Capital H of n by 2, I am talking about a capital H of n by 2, and that will be equal to 0 whenever n is even. So therefore, since here n is odd, I substitute the values of n along with the values of h of 0 to h of 5, and therefore I see the corresponding expressions with respect to the real parts of exponentials as 1 by 11 into 1 plus 2 cos of 2 pi n minus 5 by 11 plus 2 cos of 4 pi n minus 5 by 11, and the rest of the values comes out to be 0 in this case. And here I also see some interesting representations where I have h of k value is equal to e power minus j 2 pi k by 11, therefore I substitute it with h of k here, and this can be identified as 2 pi n, and I have also changed the limits of this k from 1 to 5 to only 1 to 2, because the rest of the values from 3 to 5 is equal to 0 and exists only for 0, 1, 2 here in this case. Therefore I substitute those values in the expression that what we have taken into consideration here, and therefore substituted those values and was able to see the magnitude, the h of n impulse response is represented using this expression, and calculating the real parts of those exponentials, it will be cosine values and therefore represented in terms of cosine equations. And moving forward, as we have already calculated the impulse response, now exploiting the symmetry conditions, h of n minus 1 minus n is equal to h of n, and with the center of symmetry lying at n minus 1 by 2, in this case it is equal to 5, I trying to calculate the various values of h of n for various values of small n from 0 to 0 to 10. For n is equal to 0, when I substitute n is equal to 0 in the above expression, I just get this expression in the form of 1 by 11, 1 plus 2 cos 2 pi 0 minus 5 plus 2 cos 4 pi 0 minus 5 by 11, and substituting all those values, h of 0 is resulted as 0.0694. Similarly, when I substitute the other values of n and also use those symmetry conditions, I see that for n is equal to 1 it is equal to minus 0.0594, and similarly for n is equal to minus 0.1094, and for n is equal to 3 it is 0.0474, and n is equal to 4 it is 0.3194. And at the center of the symmetry at n is equal to 5 we have calculated it as 0.4545, and based upon these all these values that what we have calculated so far and exploiting the symmetry conditions of the impulse response, now I represent n is equal to 6 to 10 in terms of those calculated values itself, and h of 6 becomes is equal to h of 4 based upon the symmetry, and therefore this is represented as 0.3194. h of 7 is equal to h of 3 based upon the symmetry, and therefore it is equal to 0.0474, and similarly h of 8, h of 9 and h of 10 are also represented based upon the symmetry and respectively equal to those values of h of 2, h of 1 and h of 0. Once we are able to calculate the impulse response values, now I represent the transfer function of the system h of z in terms of the impulse response values, and as a causal realizable filter from sigma n is equal to 0 to n minus 1 h of n into z power minus n. Since here capital N is equal to 11, this comes out to be n minus 1 is equal to 10, and I substitute various values of small n and exploiting the symmetry values, and since h of 0 is equal to h of 10 and h of 1 is equal to h of 9 and h of 2 is equal to h of 8 and so on, I group those terms and write the expression in this way. Substituting the values of the impulse response, I get my transfer function in this form: 0.0694 into 1 plus z power minus 10 minus 0.054 into z power minus 1 plus z power minus 9 and so on. And this serves as the center of the symmetry with the value lying at z power minus 5 multiplied with the coefficient 0.4545. And this completes our design problem, that is finding the transfer function of the system. But however, sometimes you will also be asked to find out the frequency responses representations, magnitude responses, and sometimes you will also be asked to represent the or realize the structure of this particular transfer function and so on. And as we have seen in the last lecture, to draw the linear phase responses or the linear phase realizations of FIR filters, I ask you to once again represent the structure of this particular transfer function using that linear phase structure, and for you I will calculate the frequency response in this case, and I leave that realization of the structure as an matter of practice for you, and I just leave it as an exercise for you. And now so let us calculate the frequency response in this case, and also draw the magnitude response characteristics. Since we have considered the impulse response to be symmetric with odd numbered values, from the table that what we have written, we identify the magnitude response A of omega can be directly given as h of n minus 1 by 2 plus sigma n is equal to 1 to n minus 1 by 2 to h of n minus 1 by 2 by minus n cos omega n. Substituting all the values of capital N and small n in the above expression, we get it as h of 5 plus sigma n is equal to 1 to 5 to h of 5 minus n cos omega n. Expanding this with respect to various values of n, I observe that my magnitude response can be represented in terms of omega, something like this: 0.4545 plus 0.6388 cos omega plus 0.0948 cos 2 omega and so on. So once we are able to identify the magnitude response of the given filter, now I calculate the magnitude response for various values of omega. For I almost take those values from 0 to 2 pi, and that's the reason I have divided with respect to some pi by 16 in this case, so that my frequency response will be more clear. I have identified as many as 30 points here, so that you will have a clearer picture of your frequency response. I have substituted various values of omega from 0 to pi by 16 to pi by 16 with an interval of pi by 16. I have identified as many as 32 points between from 0 to 2 pi, and calculated the magnitudes in all those cases just by substituting the omega value with these values in the above expressions. In this particular expressions, we substitute those omega values and I calculate the magnitudes, and I represent something like this. And based upon these values, I was able to draw the magnitude response of the FIR low pass filter, and I was able to see that in the case, since I pardon this, here I am able to observe that the passband has slight fluctuations. We are able to see that it is having some ripples, which are some ripples in the passband, both the passbands, and also I am able to see that there was a transition band which has been from pass band to stop band there was a clear transition, where slowly it has been decreased it slowly here, and similarly it also has been increased slowly to those ideal conditions, and we are also able to see some ripples in the stop band based upon all those values. Since I have taken these many points, I was able to observe these ripple sections both in the pass band and the stop band section. However, if we are ignoring and if we are taking with respect to very less values, then this curve might be very smooth, and it might ignore the presence of these ripples. Therefore, I suggest all those viewers, whenever you are practicing and trying to draw the frequency responses of the FIR filters, try to identify as many points as you can, so that the frequency response will be more clear and the frequency response characteristics can be easily studied. And that's all. This completes the design of a linear phase FIR filter by using the frequency sampling method. In addition to this design problems, I would also like to add some more points related to this windowing method and frequency sampling method. Generally, the FIR filter design by using these windowing methods and frequency sampling method suffers from a little drawback, that they doesn't have any kind of precise control over the critical frequencies such as pass band frequency and the stop band frequencies mentioned in the design problem, and this drawback can be overcome only by designing FIR filters by using some another optimal equiripple design criteria or using Chebyshev approximation techniques. In that techniques, an error function will be used to approximate the ideal frequency responses in order to satisfy all those desired specifications that what we require. And those optimal equiripple design criterions are only generally used to design FIR filters to satisfy those specifications, as I said before. And this completes the lecture series on FIR filters, where we have started with simple requirements, the simple key characteristics of the FIR filters, and then we have seen different design techniques such as Fourier series method, the windowing method, windowing techniques. We have discussed about 6 important and basic windowing techniques, starting from the rectangular window, triangular window, and the class of raised cosine windows such as Hanning, Hamming, Blackman windows, and also studied about the Kaiser window. And then we have also certainly seen some of those examples using those windowing techniques and the frequency sampling techniques. And that's it for this lecture. If you have any doubts, you just comment in the comment section, and I'll be able to